Good morning, everyone. So my name is Shusuke Sakurai. Today, I'd like to introduce our new OLGA extension for water domain systems. So we developed the hydro growth model for water domain system, and the model was implemented as an OLGA extension for transient flow simulation. So as you probably know, OLGA is a commercial transient flow simulator provided by Schulze. And then, so we conducted the flow simulations regarding the natural gas hydro production test to predict hydro growth in the actual production lines. And this simulation results suggest pipeline insulation is key to reduce the hydro growth. And the simulation results also suggest other factors such as sun may also influence the plugging. So in this presentation, I begin with a very general view of offshore gas hydro productions. So in this sense, the gas hydro and offshore gas production is moving into deeper field, but this increases the production costs. So in the context of the pipelines and productions, so longer pipelines with larger diameter are required, and so the higher wellhead pressure is also required due to deep water and long distance to onshore. And in addition, the deep water results in the high pressure requirement of the high pressure resistance of the equipment, and this should make the equipment bigger and larger, and such bigger equipment should result in the higher operation costs. So to these challenges, subsea separation may be a new option to reduce the cost. And in this concept, gas water mixture. It's okay. Okay, so the gas water mixture from the well is separated in a separator, and gas or liquid are produced through different lines. And so in the gas line, in this concept, in the gas line, the lower pressure should be enough to transport gas to onshore. And the liquid line, you may need a pump, but higher efficiency of pump should be achieved due to low gas volume fluctuation in the line. But this concept may bring new production challenges, such as separation efficiency and the different volume fluctuation in the lines downstream with a separator. So in the gas line, the system should be gas dominant, but in the liquid line, the system may be water dominant. And to evaluate the production risk from wellhead to onshore, you need to consider the different processes of hydro growth. So for gas dominant and water dominant. And to this challenge, we already developed an OLGA extension, a tool to predict the hydro growth in gas dominant system. But we didn't have any OLGA extension for water dominant system. And so this work is a part of our challenge to develop a new tool, so new OLGA extension for water dominant system. And this concept should be applicable to the natural gas hydro productions because a similar concept was already employed in the actual field test of natural gas hydro productions. So in this case, gas separation and two production lines. Gas production and two production lines. And so basically, so in this presentation, I'm talking about our application of our new OLGA extension for water dominant system to the natural gas hydro production. But please remember the concept picture shown in the previous slide, and also remember that this work is a part of our challenge for the new tool for water dominant system. So moving into the natural gas hydro production. So first of all, so natural gas hydrate is a potential future energy resource, and at present, natural gas hydrates in sediment and the deep water and palm frost are regarded as most promising. And actual production tests were also already conducted and to demonstrate gas production from these hydrates. But these tests suggest new production risk. So taking an example of the natural gas hydro production with the pressurization method. So gas hydrate in reservoir is dissociated in situ by reducing the downfall pressure by pumping water from the well. But in the left here, so if produced gas is entering into the water production line, hydrate may be formed in the line. And so for these reasons, evaluation of the gas hydrate release may be quite important in the future natural gas hydrate fractions. So to sum up, there are a couple of cross-ground challenges related to subsea or well gas separation. So in fields, so unknowns in separation efficiency, different liquid hold up, downstream the gas separation, and hydrate release. And in terms of the modeling and simulations, different processes of hydrate growth should be considered, but few are available for water dominant systems. And to these challenges, so we developed OLGA model. We developed the hydrate growth model for water dominant system and conducted a steady state flow simulation with an in-house flow simulator, which was already introduced in a previous tieback simple in 2020. And after that, we developed a new OLGA extension for transient simulation based on the developed hydrate model and conducted a series of flow simulations regarding the natural gas hydrate fraction test, which will be introduced in this presentation. So first, I'll explain the hydrate growth model for water dominant system. So in general, the process of hydrate growth is categorized by the water dominant phase. And in this work, our interest is the water dominant system in which dominant phase is water. And so hydrate first, gas and liquid, gas and oil or condensate are dispersed in continuous water phase, and hydrate growth should be happens at the interfaces between gas and water, and formed hydrate may create aggregates, and aggregates may cause a flooding. So at present, our model and extension basically focus on the process of hydrate growth, while it partially considers the agglomeration process. But in future, we'd like to extend the cover range of the model and extension. So in terms of hydrate growth in water dominant system, we took a mass transfer limited approach. So in this approach, intrinsic hydro formation rate is assumed to be much faster than the gas mass transfer rate at the interface between gas and water. And so by this assumption, the problem of the hydrate growth rate can be simplified to that of the gas mass transfer. And in general, the gas mass transfer rate can be expressed by three terms. So mass transfer coefficient, gas-water interface area, and the difference in the concentration of gaseous gases at the interface and in bulk water. And these three terms are estimated with different methods. So the gas mass transfer coefficient is estimated with a small eddy cell model in which the mass transfer coefficient is connected to the strength of the small eddies in turbulent flow near the gas-water interface. And the gas-water interface area is estimated with a correlation of surface area of gas bubbles in bubbly flow. And the concentration of gaseous gases are calculated with Multiflash, which is a commercial PVT software. And in terms of the dissociation rate, it is estimated with a function of the surface area of hydrate particles and the difference in the fugacity at the system conditions and the equilibrium conditions. And this schematic shows the relationship between the OLGA simulator and our hydrate extension. So as you may know, the OLGA flow simulator divides each flow line into a finite control volumes and calculates the properties in each control volume considering the conservation laws. And if the extension is integrated into a flow simulation, the OLGA calls the extension during this calculation. And when calling, it passes properties of control volumes to the hydrate extension. And so our extension, first, the extension checks the PT constant of the control volume is inside the hydrate equilibrium region. And if yes, it calculates the hydrate growth rate. And if no, the extension checks whether the hydrate exists in the control volume. And if yes, it calculates the hydrate dissociation rate. And after that, our extension estimates the hydrate slurry viscosity because formed hydrate change the viscosity of hydrate slurry. And yes, and after that, our extension returned hydro growth rate and hydro steady viscosity to the OLGA extension, to the OLGA engine. And the OLGA engine calculated the balances of mass, momentum, and energy, considering these returns. And so moving on to the flow simulation. And the target of this simulation is the second offshore methane hydroproduction test conducted in Japan in 2017. So in this test, 2 production wells were drilled, but no simultaneous production was applied. And in this test, the depressurized method was applied with well gas separation and 2 production lines. And in this test, much gas was produced from the water production line in the gas production from 81P2. And temporary plugging of the water line also happened in 81P2. But such problems didn't happen in 81P3. But in 81P3, much sand was produced from the production wells. And considering these events, we focused on the gas production from 81P2 because our interest is hydro growth in water dominant system. And it should be noted that there are a couple of differences in the natural gas hydro production from the conventional offshore gas production. So shallow production wells, low temperature production fluid, and simple composition of production fluids. Basically, it consists of methane and saline water. In addition, this is a production test. So production rates are quite much lower than the usual conventional offshore gas production. And the left figure shows the production well and production system. And so ESP, electric submersible pump, was installed to the wellbore, and there was a section for wellbore gas separation upstream of the ESP intake. So in the design, gas and water should be separated here, and gas and water should be produced through different lines. But in actual, much gas was produced through water line. So the blue line in this graph indicates gas rate from water production line. And so during the gas production, the temporary plugging of the hose was happened. So the water production line consists of two flexible forces from seabed to surface, and one of the hose was temporary plugging during the gas production. And during this period, there was operation to remove the plug from one of the flexible forces. And this operation succeeded, so the plug was removed. So no plugging after this operation in terms of the water production line. After that, there was a period of the plant disconnection due to bad weather. So during this period, the gas production was temporarily stopped, and so the production line was disconnected at this point during this period. After that, after restart, the gas line was temporarily plugged, and there was another operation to remove the plug from the gas line. But I skipped the detail of the plugging of the gas line because our interest is water dominant system. And this is a flow line model in the OLGA simulation. So basically, I modeled the water production line from ESP discharge to surface. And the pressure is specified at the top side boundaries, and the production rates are specified at the bottom side boundaries. And valve in the line is for simulating the temporary plugging. I explained in the previous slide. So this valve is fully closed before the operation to remove the plug. But after that, it opens. And in addition, I also assumed no deposition of hydrate and no induction time. So in actual, the induction time should exist. And this point will be we will introduce more by Mark and Chelo in the afternoon session. And so the length, ID, and material of each flow lines are specified in the simulation, and ambient condition is also specified. So moving on to the simulation results, this graph shows the ESP discharge pressure of the flow simulations and production data. So overall, the model flow simulation provided a reasonable prediction of the pressure. The error is within 10% in most time. But one important point is that this valve was fully closed throughout this period in this simulation, suggesting a plug of one of the forces throughout this period. So in other words, so the plugging happened before or in the very beginning of the gas production. So this may suggest that other factors may affect plugging. So as I mentioned, much sand was produced from 81P3 prior to this production. So maybe some sand may be accumulated or may have accumulated or remained in the line, and this might have been a trigger of the plugging, although this is just a possibility at present. And in terms of the hydrate growth in the production line, it wasn't significant in the simulations. Basically, the hydrate volume fraction in the simulation is less than about 5 volume%. So this graph shows the profile of hydrate volume fraction in the line from ESP discharge to surface throughout the gas production. And blue line in this graph shows the location of the maximum hydrate volume fraction at each time. And this graph shows temperature, pressure, hold up, and hydrate volume fraction at this time, at which the hydrate volume fraction became maximum in this simulation. And the interesting point is the temperature increase in this section. So this section corresponds to the vertical flexible force sections surrounded by seawater. This corresponds to this part. And interestingly, so the temperature, fluid temperature increases due to hydrate volume fraction because the hydrogen formation is an exothermic reaction. So heat generated by hydrogen formation increases the fluid temperature. And eventually, the fluid temperature exceeds the equilibrium temperature, and hydrogen formation begins at this point. And another interesting point is the large difference between the fluid temperature and ambient temperature. So temperature difference between inside and outside of pipe because of the low U value of the flexible forces, because forces consist of plastic layers. And so this low value results in a large difference in temperature. And so this suggests low heat exchange limits hydro growth. And to discuss this possibility, we conducted another simulation. But in this case, the flexible forces were replaced with carbon steel pipes. And by this change, the U values of this section increased significantly, basically over 100 times. And this change results in a much higher hydrogen volume fraction. So in this case, the maximum hydrogen volume fraction became about 20 volume%. And this graph shows the temperature profile, temperature, pressure, hold up, and hydrogen volume fraction at the same time. So in this case, fluid temperature decreases in this section, even though much more hydrate forms in this section due to much higher heat exchange with ambient. And this heat exchange results in much higher hydrogen volume fraction. And another interesting point is that hold up is increasing to approaching to 1, and eventually it becomes 1. So it means that no available gas in the production line. So in this situation, the availability of gas limits the hydro growth. This graph shows the comparison of the two simulation results shown in the previous slide in terms of the hydrogen volume fraction and U values. So overall, so the pipe insulation significantly reduced these properties. And to investigate the sensitivity of the pipe insulations, I conducted further simulations, in which the flexible forces were replaced with a carbon steel pipe with an insulation layer made of polypropylene layer, solid plastic. And in these cases, the hydrogen volume fraction decreased much by adding a thin plastic layer, even though the value is slightly higher than that in the flexible force cases. And in terms of U values, it's still 10 times higher than the base case, as the case of the flexible force. And for further decrease in U value, the thick insulation layer is required in the simulation. But such thick plastic layer may not be practical. So rather than increasing the thickness of the insulation layer, using different materials having much lower thermal conductivity may be more practical. So in this case, in these examples, so I replace the material with amide fiber, which has 1 order of magnitude lower thermal conductivity. And by this replacement, the hydrogen fraction and U value are down to the same level of the flexible forces in this simulation. So overall, in conclusion, so we developed a hydro growth model for water dominant system, and which was for liquid dominant line downstream the gas separation. And the model was implemented as an OLGA extension for transient flow simulations. And we conducted flow simulation in terms of the offshore methane hydroproduction test to predict the hydrogen volume fraction in the water production lines. And the simulation results suggest that pipe insulation is key to reduce the hydro growth. So we observe the large difference in the hydrogen volume fraction in the cases with and without pipe insulation. And the simulation results also suggest other factors such as sand may also influence plugging. And in addition, this study demonstrated the potential of our tools for water dominant system, maybe not only for the natural gas hydroproductions, but also conventional offshore gas productions. Finally, so this study was conducted as a part of program of MH21 R&D consortium funded by METI, and I was also affiliated to JobMed, providing the data of the offshore methane hydroproduction test, and also thank Bruce and Zach for discussion of the simulation results. Thank you.